Yeah, okay. So I'm Matthias. I'm also from Qilimanjaro. I will be talking about quantum simulations of 1D fermionic systems with Ising Hamiltonians. So a little bit for the context. So in recent years, there were a series of papers that came out of D-Wave that showed that they actually performed very impressive simulations of quite large Ising systems, and got pretty good results to the degree that fairly recently they felt they could claim quantum supremacy, which so far as I know hasn't been challenged, which is quite the long lifetime for a quantum supremacy claim. But these handful of papers basically show various things. One of them being that there are large programmable devices, and that they implement Ising Hamiltonians. So Ising Hamiltonians of this form where you have like some ZZ interactions, some local fields in both Z and X directions. And these systems become more and more coherent. So you can do things that don't look just noisy, but you can actually probe the quantum physics of it. But also another takeaway from this collection of papers is even if you have an annealing device, which is originally intended for optimization problems, as you've seen many times, they can also be used for quantum simulation, which arguably is one of the first applications that was envisioned for quantum computing in the first place. And by quantum simulation, I mean you are given some Hamiltonian and some initial state, and you're supposed to prepare the state after some time evolution, or at least some sufficient approximation of it that allows you to calculate some properties of the system that you are interested in. And now the question that one might ask, okay, what else can you actually do if you have a quantum annealing device? So these machines that make optimization, well, now we want to get a little bit creative and do things that they maybe originally were intended to. And following basically Newell's footsteps, you can ask, okay, what are the Hamiltonians that we can simulate? Maybe some Hamiltonians that are not necessarily Ising ones, but something else. Do these Hamiltonians display some interesting quantum effects that are interesting to look at and interesting to show that and generate them controllably in the device? And as the title probably already gave away, this is what I'm going to be talking about, something related to this stuff. So essentially, I will propose like some method to simulate a particular type of one-dimensional system. And the method at its core is based on what's called domain-wall encoding. It's been presented in this conference at various times already. And it was originally introduced by Nick over here. And essentially how this works is, okay, you have like a chain of Ising spins. They are typically ferromagnetic coupled to each other and like on a chain, and you pin the ends. And this introduces some frustration and degeneracy. And essentially this allows you now that, okay, these the domain was basically, you have on one side of the chain all spins up, and on one side all spins down, the main wall, and then the chest is the wall between these two domains. Right? But now, depending on where the wall sits, you can implement essentially discrete variables, right, for like, a certain region. And I will try to. There we go.
Someone not sharing.
That's unfortunate. Maybe that was the brief interruption. Yeah. Oh, back to sharing?
Yeah.
Okay. I'm also now back to the speakers, which is way more convenient. All right. Yeah. So essentially, if you enforce the main wall constraint, which is implemented using like these coupling strength J, and pair this with the transverse field, you like the spins are fluctuating and they can occasionally flip or couple. And certain spins, if they flip, they incur like a very high cost. Namely, for example, if this spin here were to flip up, it would now break this, or it would now create two more domain walls, which, thanks to the ferromagnetic coupling, is expensive. So this is kind of prohibitive. But if this spin here were to flip, it actually doesn't create a new domain wall. It just moves the domain wall over. There's still the same number. It's energetically the same. So this is like a movement of the domain wall that is essentially allowed. So in a reasonable approximation, this in the ground state of this this Ising Hamiltonian with the domain wall constraints and the transverse field can be considered as a particle that's moving moving on this chain. And these type of coupling terms, now I kind of, if you, I will later give you the arXiv thing, there are also like some obviously draw the big transformation that are a little bit hiding in here, but essentially this, you can treat this one particle as a fermion. And these type of couplings that would be required to do this on a for example, flux qubit device, actually, as Martin already mentioned, actually not that easy to make because it would require like non-stoquastic couplings. But now that if you have a Hamiltonian that essentially is like a particle, or behaves like a particle in the box, you can also introduce some on-site energy. So depending on where the particle is, now you pay some energy penalty. And the way to do this is that you perturb slightly by like these epsilon values, the local couplings. And these epsilon values are then the on-site energies that you want. And this, together again with the transverse field, gives rise to this Hamiltonian where not only do we have the hopping term as before, but the particle now also moves through some one-dimensional potential. And this is something we can actually move to, or that we can promote, like something slightly more complex. Maybe we can consider subspaces of some fixed number of domain walls that we denote as M. So we look at for example, the subspace of 3 particles, and the subspace of 3 particles is actually energetically separated by by this domain wall energy penalty from the rest of the subspaces with the respective particle. And now one thing to notice is that if you project this domain wall Hamiltonian into the subspace of a fixed domain wall number, it actually is basically the same as like some fermionic Hamiltonian that's also projected into the subspace. And I'll do some error analysis using the Shaper-Wolf transformations, which is a regression theoretic approach. We can show that this effective Hamiltonian in the subspace of this domain wall Hamiltonian is basically the same as some fermionic Hamiltonian up to some error term that scales with the inverse of this coupling strength that separates these subspaces. And that introduces a couple of errors, obviously, but they go to 0 as you make the coupling strength stronger. And this now allows that, since if you do the error analysis, you'll find that the leakage probability, so the transition between the different subspaces, actually is suppressed with the coupling strength. That allows that if you were to initialize this initial state is a state of m domain walls, you can calculate the time evolution in this effective or according to this effective Hamiltonian in the subspace, which would actually correspond to a close approximation to the time evolution induced by the fermionic Hamiltonian that you were interested in the first place. And yeah, this basically allows you to do the quantum simulation part of this fermionic system that we were introducing. And obviously, it's not a perfect simulation, so there's an error term which scales quadratically over with the simulation time. So if you want to simulate longer times, you either need, or you definitely need stronger couplings to compensate for this. And one thing to note here is that if you wanted to do a gate-based version of this same simulation, the Chopper error would also scale with the quadratic to the time. So unfortunately, we do not really, in terms of time, gain a lot by this trick, which was a little bit of a hope that I had when I started this project, that since we now stimulate analog simulation or analog evolution by an analog system, that we would find that this is better, but it ends up being the same, which also means it's not worse, which is something. Then depending on the device that we have, strong couplings may actually be also a challenge. So there's some not super scalable tricks that you can apply. Maybe you can rescale the parameters of the Hamiltonian that you want to simulate by some factor alpha larger than 1. And at the same time, increase the time, right? So the unitary will be the same that you're simulating. But it turns out, as you do the math, that even with a constant domain wall coupling, you can reduce the error of the whole simulation. So it basically allows you to effectively make the coupling strong. And if you want to simulate some t evolution time up to an error, like to an allowed error epsilon, you would have to choose some t simulation time that again grows with the square of the time that you want to simulate. But it's actually relatively harmless with respect to the error. So if your controls are precise, then you can actually also get away with not that strong of a coupling. And okay, so far to the theory. Now let's maybe go back to designing the Hamiltonian that we simulate. So what we discussed so far was, or what we can do. So now, for now, is a Hamiltonian, and we're not sharing it. That's what I thought. Yeah, I do apologize. I have no idea where this is. Anyway, so we can do a Hamiltonian look like this, right? We have a Hamiltonian with some hopping term, with some hopping amplitude, usually for t, and some on-site energies. Now, this is not like, well, this is a relatively simple system. We would like to go slightly more complex. And this is allowed by introducing nearest-neighbor coupling. So before we looked only at like an Ising chain with nearest-neighbor couplings that enforced this domain wall constraint. Now we introduce nearest-neighbor couplings, and we choose them in a particular way. Basically pops out of the math to do it, and particularly what it's like the relevant factor is like this Vn, because this, if you do it like this, will turn into nearest neighbor interactions of domain walls on this chain. So before we had, even if you initialize several domain walls, they would bump into each other and move apart again. But now you can also make them interact if they are sitting next to each other. And combine this now with depending on your device, if you have the ability to tune the local field or the transverse field also, you can additionally to the nearest neighbor interactions of the particles, you can also have like some disordered hopping tools if you want. And putting the Hamiltonian once into full glory, it's actually not as complicated of a system as like several lines of math would make it seem. It's very simple, just transverse field, local nearest neighbor interactions. That's actually all that's contained, or that's all that's required. And if you choose these parameters in these particular ways, what you can effectively simulate is a fermionic Hamiltonian as this shape. So hopping, on-site, and nearest neighbor particles. And the interesting thing is that these, like the hopping energies, Tn, the on-site energies, epsilon, and the nearest neighbor interactions, V, those are actually, depending on your device, constraints, are in principle freely tunable. And that's already a pretty large class of systems. So you can actually investigate various canonical models of many-way physics. And I will, for the sake of time, very briefly run through some of those. So one model that we looked at is the SSH model, which has like a relatively simple Hamiltonian like that. So H just also one-dimensional system where the hopping energies are alternating, or like they have one link has a stronger hopping energy than the next one, and then the repeats. And this is like a very canonical model for investigating topological phases, because depending on how you choose these parameters, what you end up that you in the spectrum is like two bands, and in the band gap you get two what are called edge states that are basically localized on the ends of this one-dimensional system. And what you can basically see here is the eigenstates of the domain one Hamiltonian and the spectrum for various coupling strengths. And as you increase the coupling strength for the domain mode coupling, you see that the operator fidelity between the Hamiltonian that you would like, the H Hamiltonian and the domain mode Hamiltonian, they become the same. So that's a system that is that could, for example, be relatively easily simulated with this domain mode approach. And another system that we basically reproduce the results from this paper here, which looks into inhomogeneous XXZ models, particularly in the level statistics and some many-body localization phenomena. But it's with the domain model approach, we managed to reproduce all the level statistics for, and including like this space emission, where if you tune like this inhomogeneity parameter for details, check the paper. As you tune it up and up, you eventually reach like some phase where the level statistics go to the linear distribution and then back to Poisson. Another model that has like very dynamic properties, or the dynamic properties that we're investigating is the AubryAndre model. It's very closely related to the Anderson model, with the minor difference that this Anderson localization transition also happens in 1D, while in the original Anderson model in one-dimensional systems you would only see a localized phase space. And actually, it has like these on-site energy terms, which are these given by like this incommensurate, or have like this incommensurate periodicity, which basically just means okay, it's periodic, but it doesn't really match the chain. And the same thing is actually for the popping energies. And there are two parameters that tune, one parameter lambda that tunes the on-site disorder, and one parameter mu that tunes the disorder in the popping string. And now with these two parameters, the AubryAndre model would give rise to like a phase diagram like that, where you have like where the eigenstates are like extended, and in one phase they are localized, and then there's like this critical phase where a bunch of chaotic stuff happens. And if we reproduce this model with the domain model approach, it basically looks the same. We can simulate for like a single particle, essentially the same dynamics, the same participation entropies, and the same phase diagram. And these parameters that we can freely tune, we can also make them time dependent, which gives us the ability to also make them or drive them periodically. And that allows us to do what's called flow gain engineering. So you have like we drive the Hamiltonian periodically, and then at short times, there's an effective Hamiltonian that has properties that the original Hamiltonian didn't have. So it's like another simulation thing. And in this illustrated in this graph or in this picture here, we start out with just a chain of just an Ising chain that with this domain model approach, we couple them strongly, we can simulate some hopping terms and on-site energies. And now we drive these hopping terms periodically, basically according to this equation here, which you can read in more detail in the paper by Leonardo Novo. And this will give rise to next, or like a Hamiltonian that has like even like nearest-neighbor hoppings, which we didn't have before, with like a imaginary amplitude. So, well, yeah, that's the math of or like a hint of the math from the flow engine. But one of the interesting aspects of this type of Hamiltonian is that actually the time evolution, if you put a particle in the system, it will not run symmetrically in both directions, but it will have a bias in one direction, and that gives rise to slightly, well, not slightly, but like very asymmetric distributions of the particle. And that's something that we also can reproduce with this domain approach. So the gray shaded area is the distribution of the particle you will obtain if you just simulate directly the Hamiltonian. The orange is, which basically matches the fidelity of 99%. The orange line is just the purely Fouquet stuff. So if we had a Hamiltonian, like the fermionic Hamiltonian that our domain model approach simulates and drove that periodically, that's what we would get. And then the error that's incurred from the first step, basically, where the domain model or the Ising Hamiltonian used to simulate the fermionic one, still very closely matches the result that you would expect from theory. And yeah, so this is like now we have like an algorithm that allows us to simulate interesting many-body physics systems. We simulate also what's called like dynamical phase transitions, which is basically you look at some functions defined like this, and it gives like new divergence here if you let the system run over time. But that's actually not the key point of this investigation here. More interesting is that now we introduce dephasing and de-excitation errors on the qubits to get like some estimate how robust this approach would be to relatively realistic numbers of or relatively realistic estimates of realistic qubits. And it turns out that you obviously see an error, but the qualitatively you can still reproduce these type of dynamical phase transitions in these with this type of simulation. And that's actually the scientific part of this talk. Just a quick summary, we basically introduced that using using the main one encoding, we can tweak the Hamiltonian slightly and simulate a very large class of these type of fermionic Hamiltonians with a relatively decent error. We tested it on various canonical models that show interesting quantum phenomena, and we're looking forward to actually trying this in the lab for example, benchmarking all devices. Also, some of the experiments that Martha talked about that she was doing in her PhD that now we might be able to do with annealing. We put the preprint out a couple of months ago. Feel free to check it out. It's a little bit dense, but it's contains way more detail than what I had done. And that's it, except for one thing. I need to first say thanks to my collaborators and also people from INQA and Barcelona who gave me actually very good advice. But last thing, the INQA conference next year, we are planning to host it in Barcelona. So if you come to Barcelona, you can meet all these lovely people. As a date, we bookmark the 3rd to the 5th of November, so you can pencil it in your calendar if you'd like. And as Martha said, we have a lovely new office with an amazing laboratory. But before anybody gets disappointed, that's not our. And with that, yeah, thank you very much.
Okay. Any question?
Thank you for the nice talk. You are comparing the exact simulation and domain wall approximation, which is time consuming or which is heavy calculation.
If you do it classically, like the numerics?
Numerically.
Depends a little bit on the system and some caveats, but if you do the single particle part, you can simplify the exact model way more, then it's very easy. But for the many particle part, the domain wall is actually slightly easier because we save one qubit the way the system is designed. So in theory, can make it twice as fast. Like nothing impressive.
Okay, thank you.
Sorry, how would you do to go to 2D systems?
Yeah, probably also with cryptography engineering. So there are ways to drive the system periodically that effectively create a second dimension with some constraints on what is actually going to be the dynamics in the second dimension. But this is something that we have wanted to do this, and I don't have that many details yet. So.
So if you're talking about 2D systems, have you thought about doing a similar idea but with spin ices?
That's exactly what Andrew Bean proposed in AQC. Okay. Right? I haven't read the paper yet in detail enough. I haven't had the time. Okay. But I have it in the back of my head. I would definitely love to see.
Very cool.
Yeah, another question. Wait, let's see.
more.